Welcome to CSC 201, Lesson 4.2. This lesson will consist of practicing some well-written proofs, practicing writing well-written proofs. So each of these we're going to prove or disprove, and remember, disprove is often done with counterexample. So we're going to have to do a little thought before we start trying to prove something to determine whether or not we should try, right? Maybe it's not true. So for example, prove or disprove the difference of any odd integer and any even integer is odd. So if it says prove or disprove, we should start by trying to convince ourselves with a few examples. So we'll do like a few test cases. So the difference of any odd integer and any even integer. So pick a random odd integer like 5 minus an even integer 2. Okay, so that's 3, which is odd, which is what they claimed. So that example satisfies the statement. It doesn't prove it, but it's like, okay, it's true 4, 5, and 2. When you do an odd minus an even, you get an odd. Let's do a few more and just convince ourselves that this is worth trying to prove is true for all integers. So let's see, another odd minus an even would be 13 minus 4, which is 9, which is odd, so that satisfies it. One more. 21 odd minus 10 and even is 11, and that satisfies it too. Okay, so I am convinced that this is always going to be true. So now I have to go ahead and try and prove it. Okay, so some scratch work. The difference of an odd integer and an even integer. So an odd integer is 2k plus 1 minus an even integer, which is 2j. And we simplify this and we'd get 2k minus 2j plus 1. This bit I think is even. I can prove it's even by doing 2 times k minus j plus 1. So now I have 2 times an integer plus 1 odd. Okay. This is just scratch work, and this is often the kind of thing that you would do. You just jot this down on your paper to prove it to yourself, to show yourself that you can prove it. And then you have to write a well-written proof for an audience, right? If your teacher or a colleague needs to be able to read your proof and believe that you have proved it, whereas this is just some symbols on the page. Okay, so I need to write this out with sentences and good logical argument. So first, we write out the original statement in more formal language, which we can do in our head, right? It says for any integers a and b, if a is odd and b is even, a minus b is odd. So let's go ahead and write it out. For any a and b in the integers, if a is odd and b is even, then the difference, a minus b, is odd. Okay, so that's just restating the problem. Then we're going to say suppose the if part is true, that a is odd and b is even. Suppose a is an odd integer and b is an even integer. Then a is 2k plus 1 and b is 2j for some k and j in the integers. Thus, the difference, a minus b, which is what we're trying to prove, is odd. We're trying to show that a minus b is odd. So I'm going to say, well, let's see what we can say about a minus b given these definitions. A minus b would be 2k plus 1 minus 2j. And then this is where the scratch work comes in, right? We've already done this bit. So I can just write out most of this. Two k minus 2j plus 1, which is 2 times k minus j plus 1. Since k minus j is an integer, a minus b must be odd, right? Because it is 2 times an integer plus 1. Okay, proved it. So I just want you to see the vast difference between the scratch work and the formal proof. Okay, so the scratch work is just to convince yourself how you're going to prove it. You have a lot of the formalities in your head when you write this down. Like, you know k and j are integers, but a reader would not. You have to define k and j as elements of the integers. And a lot of other details, right, that you are holding in your head when you write this down, but when you write a proof for a reader, you must be explicit about. All right, I have a proof here that we're going to analyze for errors. Claim, for all integers m, if m square is odd, then m is odd. So the proof starts with assume that m is odd, and we've already found our error, right? When you start a proof for an if-then statement, you assume the if part and prove the then part. This has us assuming the then part, right? That's what we're trying to prove. You can't start by assuming it's true. That's the whole point of the proof, is to prove that this is true. So this is called the converse error, which is very common, of assuming the wrong thing, right? Assuming that which is to be proved. Another example to prove or disprove that there is a positive integer n such that n squared plus 3n plus 2 is prime. Because it's a prove or disprove, we should start by testing with a few numbers, right? To convince ourselves, do we think it's true or do we think it's not true? Which one should we go for, prove or disprove? So I'll choose some n's, right? So I'm going to do some tests. Let's have n be 1. I'm just going to start going through the positive integers because I'm supposed to say, it says there is a positive integer n. So I'm going to use positive integers only. And I'm just going to test a few and see if I can find one that makes this true. If I can find one, then I'm done, right? That's the proof. I just have to find that there is one positive integer that makes this expression prime. So I'll test a few and see if I think I'll be able to find one. So for n equals 1, I have 1 squared plus 3 times 1 plus 2, which is 6, which is not prime. Next positive integer, 2 squared plus 3 times 2 plus 2 is 12, not prime. N equals 3. 3 squared plus 3 times 3 plus 2 is 20, not prime. All right, let's see, one more. N equals 4. I have 4 squared plus 3 times 4 plus 2 equals 30, not prime. All right, I'm getting sick of checking these. I think I'm not going to find one. There may be one, but I think I'm not going to find one. So I'm going to try to disprove this statement. I don't think there is a positive integer. So disproving a statement means we need to prove its negation. Okay, so to disprove a statement, we need to prove its negation. So we need to prove that the negation of this. So to negate this, there is a positive integer becomes all positive integers. For all n in the positive integers, okay, n squared plus 3n plus 2 is not prime. Okay, So negating the there is becomes a for every, and then not this part becomes not prime. So for all n in z plus n squared plus 3n plus 2 not prime, which is composite. Okay. So to prove that, I need to start, it's a for every. I have to prove a for every, which means that I have to use direct proof. So I should suppose n is a positive integer. And then I need to show, NTS often abbreviates need to show. Okay, so I need to show the second part, that n squared plus 3n plus 2 is not prime. So let's play around with n squared plus 3n plus 2. See what we can say about it. I can factor it. N squared plus 3n plus 2 is n plus 2 times n plus 1. And for a number to be prime, that means that you can write it as that its only factors are itself and 1, right? So if this thing were prime, one of these would have to be itself, and one of these would have to be 1. Okay, so for this to be prime, that would mean that n plus 2 is 1, or n plus 1 is 1, which means n would be -1, or n is 0. Neither of those are positive integers. Not in the positive integers. So, so that means that n squared plus 3n plus 2 can't be prime, right? It can't be that this is 1 or this is 1 if n is a positive integer. There's no positive integer that can make that true. Okay, so let's try and write this out formally in a well-written proof. So we start with, suppose n is a positive integer. Observe that n squared plus 3n plus 2 factors to n plus 2 times n plus 1. Okay. Both n plus 2 and n plus 1 are integers that are bigger than 1, right? Because n has to be bigger than or equal to 1, right? Because n has to be a positive integer. So this number is bigger than 1, this number is bigger than 1, which means that n squared plus 3n plus 2 cannot be itself times 1. Neither of these could possibly be 1. Thus, n squared plus 3n plus 2 fails to meet the definition of a prime number. Last example for this lesson, another prove or disprove. If the sum of two integers is even, then their difference is even. So because it's a prove or disprove, we have to start with some investigation, do a little test, right? So the sum of two integers is even, then their difference is even. So let's see, the sum of two integers is even. Okay, so 8 is even. I'm going to write that as the sum of two integers, like 3 and 5. Okay. So the sum of two integers is even. Does that mean that their difference is even? So if I do 3 minus 5, I get -2. So 3 and 5, their sum is even and their difference is even. So that works. Let's do another one. I need two numbers whose sum is even, maybe 13 and 7. When I add them together, I get 20. That's even. Is their difference even? 6, yes. So the sum of those two numbers is even and their difference is even. Maybe let's check one more. Two numbers that when they add up to get an even would be maybe 10 and 10, right? I add those together and I get 20. And when I take their difference, 10 minus 10 is 0, which is even. We established that in a previous lesson. Okay, so I'm pretty convinced that if the sum is even, then the difference is even. So let's try to do a little scratch work to set this up. Okay, so we have to suppose we have two integers, a and b, and that their sum is even. And we need to show that a minus b is even. Okay, so we have two integers, their sum is even. So what does it mean to have an even sum? So a plus b is even means it's 2 times an integer. But now what I want, right, there should be maybe some algebra I can do. I need to be able to show that a minus b is 2 times an integer. Okay, so I left some blank work here, to some blank space to see if I can manipulate what I know into what I want. So remember that when you're dealing with equations, you can do anything you want, as long as you do it to both sides of the equation. So if I want to turn a plus b into a minus b, I could subtract 2b. I just have to make sure I do it from both sides. So positive b minus 2b is negative b. So this is a minus b equals 2k minus 2b. And then there's a 2 in both terms there, so that's 2 times k minus b. K is an integer, b is an integer, so we have 2 times an integer. And convinced myself it's even. I still have to write a nice proof where I explain all the details, right? I have to say k is an integer. I have to explain what I'm doing here with this algebra, why I'm allowed to do that. So I have a bunch of extra things I need to write, little details that just went through my brain so quickly that I didn't write them down. So now I'm going to write it all down formally in a well-written proof. So I start with, suppose a and b are integers such that a plus b is even. Since a plus b is even, a plus b equals 2k for some k in the integers. Now we can subtract 2b from both sides. To get a minus b equals 2k minus 2b, which is 2 times k minus b. Since k minus b is an integer, because k is an integer and b is an integer, that's both of those are stated earlier. B is an integer, k is an integer. The difference of integers is an integer. So since k minus b is an integer, a minus b must be even.